Alrighty, so this lecture I'd like to talk about circuits and circuit analysis. Specifically, we're going to deal with what's called DC circuits, where DC refers to direct current. Turns out that when you work with circuits in general, there's two main ways that circuits can run. They can either run by direct current, whereby you'll have a bunch of wires and a bunch of components in the circuit, and the current will run through the circuit moving in one direction. So for instance, if you have a circuit, looks something like this, well, the current will run through, and let's say it runs clockwise through this circuit. So the current's running like this. And it just keeps going around and around and around as this circuit is powered. And the circuit does something, lights light bulbs or turns on a refrigerator or whatever it does. There's another way of doing circuits, and that is AC circuits. And this is a more modern version of electronics, and AC stands for alternating current. And the difference is if you have a circuit that is an alternating current circuit, rather than thinking about the current running through the wires, going around and around and around forever, you're kind of jiggling the electrons that are in the wire. And so the current jiggles back and forth everywhere. It runs forward, runs backwards, and it just jiggles around. And so all the electrons are moving in the wire, so every piece of the circuit feels motion, but instead of it being a continuous motion, the electrons move back and forth, left and right, up and down, whatever it is. Okay, there's reasons that AC circuit method was created. It's more efficient, allows more fancy components to be placed in the circuits, more fancy electronics to be made. But of course, it also makes for a more complicated analysis. For now, as an introduction to circuits, we're going to focus on DC circuits. This will get you a good ways of the way into understanding how electronics work. And most of the components for normal circuits you'll be able to understand. And then later on, either in a future lecture or a future class, depending, you will learn about AC circuits and how that differs from DC and what's new and what can be done with it and all sorts of stuff. But as I said, for now, DC circuits is what we're going to be dealing with. All right, well, in order to understand circuits, we must understand what are the main concepts that are necessary, what are the things that are going to be coming up, or in a simplified way of thinking about it, what types of variables will be in our equations. Because of course, when we do an analysis of a circuit, likely we're going to be calculating something, we're going to be solving for an unknown or predicting something, and that means we're going to be using equations, and thus there are certain variables that are going to be in our equations. So what variables do we need to know? First thing we need to know is what's called voltage. Voltage has the variable V, capital V. Its unit is capital V as well, which stands for volts. And what the voltage is the potential difference. So if you imagine you have a wire and a little terminal over here, and another wire and a terminal over here, and this is connected to something, and this is connected to something over there, whatever. And you manipulate these wires by creating a very, very positive side here. You put a bunch of protons there, or you take away a bunch of electrons, however you want to make it very positive. And over here, you make this side very negative. You stick a bunch of electrons over there. Well, when you do this, what winds up happening is, as you know from electricity and magnetism, electrostatics and electrodynamics specifically, is positive and negative charges attract each other. And so, what's going to happen if you have a very positive side and a very negative side, they're going to attract each other very strongly. And in fact, the electrons that create this negative side, they're much lighter than the protons. They're the ones that are free to move through the wires. Eventually, that positive side gets so large, so positive, that it pulls the electrons over to him. And these electrons are kind of forced to be brought over to the positive side to try to negate, to try to neutralize this difference, this potential difference. It's the same as if you were to, say, have the ground and there's a ball lifted up in the air. Well, there's a difference. There's a potential difference here. This is, of course, gravitational, where the ball wants to be on the ground. That would give it the lowest gravitational potential energy. But when you lift it, you do some work, and you increase the potential difference that this ball will feel. It's attracted to the ground very strongly. In fact, if you let go of the ball, that ball will be pulled as if it's attracted to the ground until it reaches the lowest potential. The same thing is true for electrons. The difference, of course, is with electricity, there's positive and negative sources. In gravity, there's only one source, that's called the mass. So you don't have repelling and attraction. Whereas in electricity you do. If they were both positive sides, they would repel. But it's kind of the same type of thing. You set up the system such that an electric charge is so attracted to move to another position. That attraction is called the potential difference between two spots, and that's the voltage. The voltage is this kind of needing to move to the other side kind of a thing. Okay, so that's the voltage. What else is there that we have to worry about for circuits? There's something called the current. What am I doing? Current, sorry. The variable for current is capital I in physics. Now in engineering, it's actually J, or I, little I, as well. It depends on what class you're in. So if you're an electrical engineer, it's little I. If you're a physicist, it's capital I. Or if you're a graduate physicist, it's capital J. But for now, we think of it I. Capital I is current. The units of current is capital A, which stands for amps or amperes. Amps for short. And what is the current? Well, if you think about a wire, this wire has a bunch of electrons in it. And if you set a potential difference, if you set a voltage through the system, these electrons want to move through the wire. Okay? Well, if you take a piece of the wire as a starting point and another piece over here as the ending point, and you say, okay, how many charges flow through this piece of the wire per second? So that would be how much charge flows per second. It's kind of like a velocity or a flow rate. That would give you coulombs per second, where coulombs is the unit of charge. So how much charge flows per second, coulombs per second, is an amp. 1 coulomb per second is an amp. It's measuring how much charge passes a certain location per second. Okay, so it's like a measure of the number of electrons that are flowing. The more electrons flow per second, you have a higher current. And so, of course, you would imagine this is related to the voltage. If you increase the voltage, it's like you're pulling harder, forcing these electrons to want to move to the other spot faster, then you would imagine you'd have a higher current. By pulling on these electrons harder, they're going to move faster, thus more electrons can flow by per second. There's one more thing that we need to worry about in circuits, and that's called the resistance of the circuit. The variable for resistance is capital R, and its unit is a Greek letter, looks like a horseshoe, called ohms, and that's the unit of resistance, ohms. So what is the resistance? Well, the resistance is like a measure of how hard is it for this current to flow. Imagine you have a pipe with some wire, a pipe with some water, and this water is flowing through, and then all of a sudden, you maybe constrict the pipe. Maybe there's something stuck in the pipe, and so only a small piece of the pipe is open. Well, that's going to constrict the water trying to flow through. And the same thing can happen with a circuit. You may have a circuit that's just a bunch of wires, and the wires connect to each other. But then if you put something in the circuit, maybe you put a light bulb, well, now all of a sudden the electrons have to get through the light bulb to continue going. And maybe the light bulb's material is hard for the electrons to push their way through, and maybe there's a lot of friction involved. Maybe that friction steals energy from the electrons trying to flow. That energy is in the form of heat. And so the material of the light bulb heats up so much that it gives off energy. It gives off light. And that's, of course, the old incandescent light bulbs. That's exactly how they worked. The electrons are passing through the material of the light bulb. There's so much material there. There's a lot of friction. As these electrons try to push their way through the metal heats up because of the friction, and it heats up to such a hot temperature that it glows, and that's the light we see. Well, obviously, that resists the ability for these electrons to freely move through the wire. And so anything you put into the circuit, even wire itself, if you've got a really, really, really long wire, that adds to the resistance because that's more metal these electrons have to push their way through. In fact, I don't know if you've ever used one of those electronic deep fryers, but if you ever try to use an electronic deep fryer, you cannot use an extension cord to plug it in. If you've ever tried using an extension cord to plug an electric deep fryer, you'll find that the fryer never gets up to temperature. And that's because the extension cord itself is so long, there's so much wire, that the current is reduced because of the extra resistance in that wire. And so you can't get enough power into that electric deep fryer to heat up the oil. And that's just wire, much less if you put in a radio or you put a light bulb or a refrigerator or a TV. All these different things that you may put into a circuit increase the resistance, lowering the current, reducing how efficiently these electrons can flow through your wire. So that's something that needs to be taken into account. And in fact, these are the three main characteristics you'll have to worry about. The voltage, which is like how hard the electrons are pulled through. The current, which is a measure of how fast the electrons are moving through, how many electrons per second. And the resistance, how hard is it for the electrons to try to push their way through. They're all related, and they're related by what's called Ohm's Law. This is the main equation we're going to deal with for circuits. And what it says is the voltage, V, is equal to the current times the resistance. Nice, easy little bitty equation here. And what you're going to find is for most of the problems we do when we have a little circuit that we want to analyze, this is the equation you're going to be using. This equation is true for the circuit as a whole. So if you're talking about the total voltage of a circuit, it's the total current times the total resistance. Or if you're just looking at a little part of the circuit, so the voltage at this one part is equal to the current at that one part times the resistance at that one part. So this equation will hold no matter how you're trying to analyze the system, and you'll see what I mean as we get into examples. So let's look at an example. Let's say we have a circuit. Here's a circuit. Now, in order for you to understand how to analyze a circuit, of course, you need to know what these drawings mean. So obviously, it won't do good for a person when they're trying to study circuits or analyze circuits to try to draw exactly the actual realistic look of a circuit, because that may be kind of difficult to do. So instead, what people do is they draw circuit diagrams. A circuit diagram is basically like a simplified version of what you're looking at. Kind of like if you look at the blueprints of a building. The building, of course, is a very complicated thing. The blueprints, however, are the most fundamental simplified view of what it is you're about to build. And it gives you all the information you need to be able to build it. Well, the circuit diagram is the same thing. So in order to understand what the circuit diagram says, you need to know what are all the different things. Firstly, this symbol here is called a voltage source. So the straight lines, these vertical lines, are the wire. And this thing that has a long horizontal line and a short horizontal line is the voltage source. You can think of it kind of like a battery. Or maybe it's the outlet in the wall. It's where the voltage, where the power is coming in. So that's what causes the voltage. So generally you'll have some V, like 10 volts. That's telling you this source of voltage is supplying 10 volts to the circuit. The other thing you need to know is the thing that looks like this. So of course, this and this, these are wires. And then this part of it here, looks like a sawtooth type thing, is called a resistor. It is the element that you stick into the circuit which causes a resistance. Now, it could be a light bulb, it could be a radio. Obviously, when you're drawing a circuit diagram, you're not going to draw a refrigerator. Instead, you're going to say, this resistor that I've drawn as a simplified version stands for the refrigerator or stands for the lamp. And so you would have something like, some number of ohms. So maybe, let's say, 5 ohms. And then there's some current running through this circuit, running around, let's say, clockwise. some current running through the circuit. Generally, what we say is the direction that goes from small to large is the direction of the current. So in this drawing, the way I've drawn it, imagine the current going clockwise around the circuit. Now this is a contention depending on who you're learning circuits from. And the reason is because at the end of the day, there was a confusion from the very beginning of electricity about what the current represents. Benjamin Franklin felt, who was the person that discovered electricity for us, felt that electricity running through the wire was the protons moving through the wire, and that's what's causing the current. And so all of the circuit diagrams and things that developed from that assumed that it's the direction that protons flow through the wire. Unfortunately, what we found since then is that no, in these metal wires, the protons don't move. They're part of the nucleus. The protons stay still. What moves are the electrons. And so what you will find is, given a circuit, if we say the current flows this way, what is actually happening is the true electrons are actually flowing the opposite direction. Now, that's the standard. The standard is, if we say the current flows clockwise, we understand deep down that in actuality, the electrons are flowing counterclockwise. And we just have to understand that. What you'll find is, depending on who you learn from, they don't like that. And so they teach it the opposite way. They say, well, if the electrons are flowing counterclockwise, that's the direction of the current. And so those people would say, no, 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 the current is actually flowing counterclockwise. So you just have to be careful when you're looking online or you're looking in certain textbooks. Some people will say the flow of the current goes from the small side to the big side. Other people will say it goes in the opposite direction. It doesn't matter, because at the end of the day, all the numbers will come out right as long as you stick with whatever standard you decide. I, because of the classes I've taken, both in electrical engineering and physics, am going to use the standard that is, the current goes from the small to the big on that voltage source. And I just understand that the electrons go the other way, and I don't worry about it. All right, anyway, what question could I ask about the circuit? I could ask, what current flows through this circuit? Well, I only have one equation to use, and that says V equals IR. I'm looking for the current, so I solve it. I say I is V over R. And if I want the total current flowing through the circuit, then I need the total voltage of the circuit and the total resistance. So I'll look at my circuit. There's only one resistor. There's only one voltage source, so this is easy. The voltage is 10. The resistance is 5. So 2 amps is the current. Nice and simple. Will it always be this simple? Obviously not. In actuality, we're going to have circuits that are much more complicated. And of course, if you get into higher level courses, you're going to get very complicated looking circuits. So we're going to have to understand, how do we analyze more complicated circuits to figure out what's going on? You know, can I predict, if I stick this kind of a battery in, will that supply enough current for my circuit to turn on? Or if my radio goes out, what kind of a capacitor or what kind of a resistor should I put in to make sure that I can tune into the right radio stations. So, how do things get more complicated? Well, for now, we're only going to deal with circuits that have a single source, a single voltage source. However, we will allow there to be multiple resistors. So for instance, what if I gave you a circuit that looked like this? (10 volts). Let's say this is 3 ohms and this is 2 ohms. Calculate the current. How can we solve this? Well, you're a scientist, or you want to be a scientist. You should be thinking about it. You should use your intuition. Try to think your way through, how should I go about trying to answer this question? What are the possibilities? Well, if the current is trying to flow and it's got the same amount of potential, so whatever's pushing my electrons, that's just pushing it. And what I'm trying to get through is not just one resistor, but two, then it would seem that maybe it makes sense that I just add the resistance of each of the resistors, and that'll tell me the total amount of resistance I have in my circuit. If I have one resistor, that's the resistance. If I have two, well, maybe if I add them together, it's the total resistance. Well, let's see how that would work. Let's say the total resistance here would be the first resistor plus the second resistor. So I'd say resistor 1 is 3, resistor 2 is 2, and so the total resistance is 5 ohms. And then I could say V equals IR, which tells me I is V over R. The total voltage is still 10, and now the total resistance is 5. And so I get a total of 2 amps flowing. Okay. Now, let me ask you a separate question before we discuss whether that's true or not. This is a possibility. What about this problem? Let's say I've got 3 and 2, like this. So again, I have a circuit, and in this circuit I have 2 resistors. Should this circuit act like this circuit? Should they act the same way? One voltage, 2 different resistors, they're both 3 and 2. I'm trying to push my current through. Should these 2 circuits give rise to the same current? We need to think about it. Well, let's look at this first circuit and see what can the electrons do. The electrons are trying to flow through. So here's a little electron, he's flowing through, he's moving along. He comes here, he hits the resistor, has to force his way through. Then he gets out of the resistor, and then he hits the next resistor, he has to go through. Then he's through, and he flows around. So this poor electron has to go through both the 3, and he has to go through the 2 afterwards. So that electron feels the effect of both of these resistors. Now let's look at what an electron would feel when it goes through this circuit. So the electron's going through, he hits this point, and then all of a sudden, here, he's got an option. He can either flow up this way or keep going straight ahead this way. Now, of course, if we're talking about something like quantum mechanics, then we've got some real funny complications going on where maybe the electron does both. But we're not going to get into quantum mechanics. We're going to deal with normal classical circuits. This electron has to choose a path. He can't go through both. let's say he chooses the top path. Well, then he's going to hit the 2, he gets past the 2, he comes over here, and then he just keeps on going till he gets back to the end. If instead he decides to go straight, if he goes straight, he's going to hit the 3, gets past the 3, and then he just continues along. So depending on which path this electron takes, he might hit the 2, or he might hit the 3. But he will never hit both. So he should not feel the same thing as the other circuit. So then I would imagine this bottom circuit should be solved differently. Now, with that said, now that I hope I've convinced you that there should be a difference between these two circuits, I'll give you what the answer is. The answer is this. There's two ways of combining resistors into a circuit. If you've got multiple resistors in your circuit, they can be connected either in what's called a series connection or a parallel connection. Okay? A series connection is like the first circuit. You have a resistor, then you have just nothing but wire, and then another resistor. So here you go, you got a resistor, and then nothing but wire, and then another resistor. And there's no choice but for that one electron to have to go through both. That's a series connection. If you have a series connection, the total resistance of adding up all of the different resistors that are connected in series, because of course, maybe you have 2, maybe you have 100. But however many you have, if they're connected in series, then to get the total resistance, you just add up each one individually together. And what you might find in a textbook is a nice fancy way of saying it. The sum over I, I goes from 1 to n of R sub I. Okay, that's a fancy way of saying just add up all the resistors together. However many there are, if you have n resistors connected in series, then it's R1 plus R2 plus R3, dot, 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 till you get to Rn. Parallel. What's parallel? First thing I want you to understand is parallel does not mean they're drawn parallel to each other. Now, it happens that the way I drew it here, the 2 and the 3 are drawn parallel. But please, if you learn anything from this lecture, make it be you do not get fooled that just because 2 resistors are drawn parallel to each other, that does not mean they're actually connected in parallel. What makes them connected in parallel is, at some point, an electron would have to choose one path or the other. So that electron will never go through both. It'll either go through one or it'll go through another. If it's connected like that, the total resistance, 1 over that, okay, so 1 over the total is 1 over R1 plus 1 over R2. And if you have more than 2, then you just keep adding them. So this one's weird. This one, you're adding up the reciprocals. So if I were to do it for this particular one here, I'd say 1 over R total is 1 over 2 plus 1 over 3. And now here's the tricky part. Pay attention to this, please. If I add 1 over 2 plus 1 over 3, what do I get? I get 5 over 6. Okay? Now, what is 5 over 6? 5 over 6 is not the resistance. 5 over 6 is 1 over the resistance. So in order to get the resistance, I need to do 1 over that number. So our total is actually 6 over 5, or 1 over 5 over 6. which is 6 over 5. Okay, so that's very, very, very easy place to make a mistake, especially on a test where you may have a deadline and you have to finish the questions quickly. You say, oh, these resistors are parallel. Let me get the total resistance. 1 over 2 plus 1 over 3, that's 5 over 6. So the total resistance is 5 over 6. No. 1 over the total resistance is 5 over 6. Once you get that number, take its reciprocal. So in this case, the answer is 6 over 5. So there you go. Given a circuit with a whole bunch of resistors in it, if those resistors are connected in series, what does that mean? That means when an electron tries to flow through, it goes through the first resistor, and then continuing along, it has to go through the next resistor with no choice. That's called series. To get the total resistance in series, you just add the resistors up. R1 plus R2 plus R3, dot, dot, dot. If instead you have resistors that are connected in such a way as to be parallel, which means when an electron hits this part, it can either choose one path or the other path, then they're parallel. To get the total resistance for him, it's 1 over the total resistance is 1 over R1 plus 1 over R2, dot, 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 dot. Now, I'm going to warn you right here. If you look online or you look on the web or YouTube, you might see this equation. R parallel is R1 times R2 over R1 plus R2. Okay? And if you look, that actually happens to work for our example over here. My warning to you is to not use this. It is true and it does work, but it only works if what you have is 2 resistors in parallel. If I give you 3 resistors in parallel, then you can't add to it by R3 here and plus R3 here. That doesn't work anymore. And I've found too many students trying to do that. So I don't teach this little shortcut calculation. It does work, and it works perfectly fine if you use it when you can. What I prefer is that you use this calculation because that always works. As long as you do it correctly, you can always use this calculation. And in fact, when I do the calculation, this is how I do it. It's the more basic, kind of grammar schooly way of doing it, but I know if I use it, I'll never be wrong. However, with this red little shortcut equation, if I try to use it on a system with more than 2 resistors, it's going to come out to be wrong. And so I'd rather not even worry about when can I use it or when can I not. Let me just use the basic one and be done with it. Another thing I want you to be careful about is, you tell me, is this connected in series or parallel? R1 and R2. Is that series or parallel? Okay, I think you have an answer. Now what about this one? Is this series or parallel? Okay, so this is number 1, this is number 2. What about this one? Let me redraw it. Okay, is that series or parallel? And the last one. So I have 4 examples here. And I want to know R1 and R2 for each one of these 4. Is it series or is it parallel? Let's look at the first one. This is series. What about the second one? This is series. And I'll explain why. What about the third one? This is parallel. And the fourth one, this is series. Now, it's my experience that the majority of class gets this one wrong. Number 4, people say parallel a lot. And the reason they say parallel is because, of course, R1 is drawn parallel to R2. And they conflate being connected in parallel with being drawn parallel. It's two different things, and it's just the fact that it's the same word that confuses people. Let's look at each one individually. Notice what an electron does for circuit 1. Electron comes in, it has to hit R1 with no choice. Once it gets past R1, it keeps going, then it has to hit R2. So that electron has no choice but to go through all of them. That's why he's series. Let's look at circuit 2. Same thing. Electron comes in, hits R1, leaves, then hits R2, and leaves. Has no choice but to hit both. Now let's look at 3. Here's an electron. The electron gets to this point, and then all of a sudden has a choice. Do I want to go to R1 or do I want to go to R2? Let's say it goes to R1. Once it leaves R1, it's done and can just go through the rest of the circuit without ever touching R2. And of course, the same goes for R2. If it goes down the R2 path, then it could just leave R2 and go the rest of the way without touching R1. Since this electron has a choice and doesn't have to go through both, it's parallel. Now let's look at 4. Why is 4 series and not parallel? Well, what does an electron do? Electron hits here, must go through R1, continues on, continues on, continues on, and then all of a sudden it must go through R2. So this is exactly the same drawing as that, and it's the exact same drawing as that. And in fact, what you're going to find is for circuit diagrams, you're allowed to stretch the wires as much as you can. These 3 drawings are one drawing. That's not 3 different circuits. That's exactly the same circuit. So if I were doing a circuit diagram of an actual circuit that I'm looking at, I could draw it as number 1, number 2, or number 4, and they're all correct. They're all true. They're all the same thing. It's just what I do from number 2, I take this piece of the circuit and I stretch it around to over here, pulling this wire, and what that does is it creates that circuit. And then to get to number 4, I just keep grabbing onto this resistor, pulling it over here, stretching out this wire, and that's what gives me number 4. So number 1, number 2, and number 4, they're all exactly the same circuits. But the big key I'm trying to make you see is number 4 here, even though those 2 resistors look like they're drawn parallel to each other, you have to be careful and see that actually they're series. And that'll be a big deal when you're working more problems and you're working some homework, and I say, what's the total current running through the circuit? If you can't tell if resistors are in series or parallel correctly, you're not going to be able to do Ohm's Law. Because the first step of being able to do Ohm's Law is, can you combine the resistors to get a total resistance? But I hope with this little example, you now know what to look for. Just pretend you're a little electron, follow the electron through and see what it does. That'll help you figure out when things are parallel or series. Anyway, this is the basics of what we're going to do with the circuits. Of course, look out for the next video. I'll do some examples of more complicated looking circuits with more resistors in it. How do we combine resistors together? Once we combine them together, how do I find the total current or the total voltage or whatever? But here you have the basics. The big equation, Ohm's Law. To be able to use Ohm's Law, You have to be able to take a circuit that has multiple resistors and either combine them in series or combine them in parallel. Once you've done that, you now have a total resistance. You can calculate the total current. So that's what we're going to be doing. So, until next time.